It's great to be here. Thanks for inviting Amazon Web Services. I'm subbing in for one of my colleagues. I have security in my title, but I've actually mostly worked as sort of a generalist in the technology space for AWS. I've been with AWS for 8 years, well, almost 8 years. Things happen so fast there, we say it's like dog years. So I've actually been there 56 years at Amazon Web Services. Speaking of things going fast, I had a 30-minute slot this early afternoon. Flight was canceled from Dulles, so I got a 20-minute slot now, so we're going to go really fast. So we'll talk about hardware innovation. I'm going to start with sort of the in-the-cloud story, and then I think you'll see how that is going to percolate through a lot of other parts of the general ecosystems in which we operate. Let's start with the Amazon EC2 Nitro system. So this may seem a little off the topic, but go back a few years to our very successful virtual machine service. We did virtualization the way everybody typically still does today, which is running a privileged copy of an operating system called a DOM0 or some equivalent name, which does a whole lot of the work, especially supports the device models for virtualization. And that's a big, complicated piece of software, and there are lots of things about this we didn't like. How can we do this better? And we wanted to simplify the design, remove a lot of the processing from the main system, and essentially take advantage of accelerators, accelerated hardware, and special capabilities that we could add to make this virtual machine service work a lot better. And really to apply the microservices concept, can we build little modules, building blocks, little bricks that we can assemble together, Lego bricks, to build better systems for supporting our cloud platforms. And the kind of a gleam in the eye was a special hardware to do this. So we did this on a sort of step-by-step basis. The first thing we did was we took on the device model for virtual networking. So VPC is the name for our virtual network. It's an overlay network. It takes every packet that you send to us, wraps it inside another packet, sends it on after a bunch of security checks, and et cetera. There's a lot of processing involved in managing that virtual network. And so that was the first thing we did, was to offload the processing of the virtual network to essentially a coprocessor. And we used off-the-shelf hardware for that. The next step we took was to try to offload the device model for what we call elastic block storage, which is a cloud-based block storage for virtual machines. So it looks like a local hard disk, but actually is a fleet of servers that do block stuff for you. And this was a really important step for a couple reasons. First of all, I don't think anyone in the industry had done this to this point, but also, critically, it led us to a vendor out in the industry who had built what was in a very bleeding edge technology, which is called the Non-Volatile Memory Express NVMe. They built essentially a software-defined implementation of NVMe running on a chip. And that was really interesting because we thought NVMe looked like it would have a long lifespan. It's a very efficient model for doing block I/O. And this vendor was a vendor called Annapurna Labs. And we liked Annapurna Labs so much we bought them. So Amazon now has a fabless silicon division that does custom hardware for us. Next step was instant storage. I'm going to have to go very fast through this, but eventually, when we get to about a year and a half ago, we launched the full Nitro system. And this is a virtual machine system in which the main board, the motherboard, essentially does almost nothing except just run VMs. It slices up memory and CPU, hands that out to VMs, sets up some secure channels across the PCIe bus for hardware accelerated interrupt handling, and then pretty much gets out of the way. And all of the device models are implemented in hardware, in custom hardware, silicon that we develop with Annapurna Labs, and of course, associated custom software. So these Nitro chips, there's one main chip, the Nitro controller, that sort of orchestrates the whole system and provides the secure foundation for the system. It then essentially boots and runs these other Nitro computers that do the virtual network wrapping, the virtual block storage, and even local storage in these devices, in these computers. There are NVMe local storage devices, but they're not connected to the PCIe bus of the main board. They're connected to a Nitro computer, and the Nitro computer is connected to the PCIe bus. And so when you write blocks to local NVMe storage, you're writing to another computer, which does line rate encryption and all kinds of other stuff for you, and then writes eventually to the device. Even though they're all in the same box, essentially you have a cluster inside that device, which is implementing all this technology. And the beauty of this is we can completely get rid of that DOM0. So now there's nothing running on that main system except virtual machines and a little bit of our software and a very thin hypervisor derived from KVM we call the Nitro hypervisor, which enables this magic to happen. So of course you can slice it up still, and the hypervisor will do the slicing and dicing for you. My button works. You can slice it into 6 VMs. You can slice it into 48 VMs, and we'll allocate the appropriate resources. We don't ever overcommit in EC2, with some exceptions I'll put to the side, but in general, EC2 instances, when we say we're giving you a certain amount of storage and CPU, that's yours for the use, and it doesn't matter whether anyone else is busy or not, you get that allocated to you, hard allocated. Now, you look at this design and you might think, well, why do you need a hypervisor? And that's a good question, because you don't, and so we have what's called a bare metal instance type, where the customer gets the whole main board, and they can run their own hypervisor, they can run their own operating system, and what they see from their operating system are what looks like a regular network controller, some NVMe devices, et cetera, but it's on those separate computers in the same physical box where all of the EC2 virtualization magic happens. So the virtual network, virtual storage, CloudWatch metrics, et cetera, et cetera. There's all kinds of stuff you need to do in a virtual machine service. And I won't go into the gory details, but critically, now we have a whole new kind of security challenge here. Normally, the hypervisor is what prevents customers from leaving behind little special favors for the next customer, right? The hypervisor will prevent you from writing to firmware, for example. Now there is no hypervisor. So we had to do some more innovation to make it so that the software running on the main board cannot update any of the firmware. And let's assume that is broken because you want defense in depth. When the systems boot, the Nitro controller scans all the firmware and validates that it's all valid. And it holds the system board in reset, scans all the firmware, and then allows boot. So we have some protections against the customer who's trying to leave special gifts for the next customer. I mentioned these are kind of main boards kind of generically. Now we support both Intel chips, AMD, and also, as I'll mention in more depth in a second, the ARM-based processor we call the Graviton processor. So just to kind of drive this home, I'm going to walk through a EBS attach very quickly. So again, I hope you know something about AWS. If not, sorry, but this would be like I call an API and say, give me another virtual volume. Just attach a 1 terabyte volume to my virtual machine. So you call the API you call the endpoint, the API runs some internal microservices, calls the control plane reaches down through the Nitro control plane to send a message essentially to the host and says, hey, customer wants a new storage volume of a certain type. Now what happens there is the local Nitro controller will call the special computer that runs EBS storage and say, hey, why don't you instantiate a new virtual disk on the system. And what actually happens next is that the EBS controller computer, which looks to the main system as an NVMe device, it just does a PCIe hot plug event and says, hey, another NVMe device, I'm here, you can initialize me. Mainboard sees that and initializes it. If there's a hypervisor there, it does the initialization, hands it off to the VM. If there's no hypervisor, it's just a normal NVMe device that shows up or looks like one, even though it's actually implemented across the network. And that's how we can create essentially virtualization without virtualization in this environment. Bunch of nice benefits. I want to briefly go over these. Actually, I'm running out of time. So, you know, security benefits, I mentioned a few. There's really cool performance benefits too. For example, the fact that we can unload, offload to custom hardware built and designed by Annapurna Labs and running our software, the fact that we have you know, full line rate device encryption for all of the storage, all of the networking. Our latest instance types have 100 gigabits per second of networking, but they can encrypt all of that at line rate. So when one of these modern instance types, you can't do a big bang upgrade. We still have a lot of older types that don't have this feature, but over time they'll all gain this feature as we add new systems. So when an N instance type, one of the new ones, is talking to another one of those, they encrypt all the traffic between the two of them all the time at up to 100 gigabits per second. And there's a whole nother talk we could give, or discussion we could have about how do you get really high scale and high throughput using this sort of commodity technology on these systems without using something like InfiniBand or some other relatively expensive, relatively non-commodity, relatively non-scalable technology. You're not going to find too many InfiniBand networks with thousands and thousands of nodes attached to them with full line rate speed between them. So we have some really cool technology which essentially does the kind of spread thing that you would expect. So we have a CLO network, which is a type of topology where every node can talk to every node at full speed. We have flows up to 10 gigabits per second, and then we have technology which will take an MPI application or something like that and essentially break all of its calls into multiple flows, UDP, like a reliable UDP datagram, send that across this giant network to any other node. And so the nodes can talk to each other at super high speed, but their actual connections are streaming over multiple ones of these underlying connections. And that way you can use commodity technology like 25 gigabit per second Ethernet for really cool technology. So very briefly, we have taken that learnings from the Annapurna experience. The hardware, the custom hardware I was talking about is a kind of hybrid. It includes some ARM cores, well understood technology, easy to program, lots of good tools for that. It includes some custom components. We took that sort of ARM processor and we turned that into a customer-facing type. So now you can launch an EC2 instance with an ARM processor with 64-bit, I think it's 16 cores, lots of memory. So we're really the first cloud vendor to provide non-Intel compatible capabilities in our virtual machine platform. So we have this instance type and lots of software types for the ecosystem, et cetera. Okay, so that's all kind of background really for the next couple of, or the second half of the talk, which is, that's all cool stuff in the cloud, it's all custom hardware. You kind of see it, you can sort of get some of the semantics that are exposed through to you as a customer. But what about kind of going beyond that into the outer larger world? And that's what I want to talk about. Actually, one more thing, again, starting in the cloud. So we've also announced another chip, the custom chip we've designed, which we call Inferentia. So NVIDIA is doing a great job for their super powerful, super expensive capabilities for GPUs, which our customers use massively for building and training models. But inference is, in some ways, an even more critical thing because for every model you build, there's going to be millions of times that you run inference with that model. So we're building a special chip just for the inference phase of a deep learning network. And that was announced last fall and will be shipping this fall. And we think we can really get some great outcomes from this, driving the price down, driving the capabilities up, building a whole integrated software stack so that you have things like a special adapter that can decide whether to run code on the host processor, the main processor, or on these Inferentia chips, debuggers, and tools to make this a really efficient system. And this will be available in private beta fairly soon. And we think we'll get some really great results from having a custom chip for inference. Now, initially, that'll be in the cloud, but now we'll talk about some things which you could maybe speculate might result in you thinking that it could end up outside of cloud as well. So speaking of outside the cloud, I want to talk about a few things we're doing in the outside the cloud space, which is kind of a big area for us as we grow, and that is the three different kind of categories. I want to start with something called AWS Outposts. So Outposts was announced also last fall. That'll also be available toward the end of this year. Essentially, this is an ability to take like equivalent of one of these Nitro systems, a rack of gear that powered by Nitro, and you can call an API, which is an ordering API, and we ship you one, and you can then deploy it in your environment. It builds a there's some basic stuff you have to do there. You have to give it power and networking, obviously. But once you give it networking, we'll build a encrypted tunnel back to the cloud, and then we can manage and keep that thing as a fully managed service on premises. Same APIs. You essentially create like a new subnet in your VPC, which is this on-prem subnet, and everything else works pretty much the same. So you, again, order the thing, connect, and launch various kinds of services. So you'll be able to, just pretty much like a normal EC2 environment, but again, almost think of it as like a special availability zone. With multiple accounts can be supported, multiple VPCs in that environment, all the EC2-based core services, EC2 EBS, VPC. But also we can run other EC2-based services there, like our relational database service, various things like our container services and so forth. And then you'll also be able to reach the cloud services as if you were local to the cloud, the big difference, of course, being higher latency. But otherwise, it will have a very common experience. And there's some new features there that are designed to allow you to connect to the local network, because one of the primary purposes of this technology is to provide very low latency to the local network. So you'll have either full, layer 3 routing, or you can do NATing and so forth from these environments. So again, standard APIs and SDKs, et cetera, et cetera. What else? So for a while now, we've been shipping these devices we call snowballs. And these essentially are portable compute and storage devices that ship around. They have, again, you can literally call an API and it will be shipped to you. It has a software-defined shipping label on the device, so you eliminate a whole bunch of errors in that world. And basically allows you to move data back and forth to the cloud very efficiently. That was the first use case, the Snowball. Then we added compute power to these devices. So there's something called Snowball Edge, which has pretty significant capability for running virtual machines or our Lambda Greengrass service. And again, we've recently added GPU support for those. So basically, you can build an AMI like an EC2-based compute thing, and then you just say like right-click deploy, and it will go onto the Snowball. The Snowball ships to you. And these really have some great use cases, whether it's oil and gas industry, hospitals, military, et cetera. And again, this is in areas where, initially there's a lot of sophistication in the security and tamper resistance and multiple layers of encryption, et cetera, because when the devices are in transit, they're outside our control, they're outside your control, so we have to do a lot to ensure that that an attacker that gets a hold of one of these while they're in the distribution or in the shipping channels doesn't able to get access to your data. And we have a really good story around that, which I won't go into the details. But over time, we want to add more custom hardware capabilities to these things as well. This is kind of the portfolio, including all the way up to a semi-truck trailer version of these. We literally deploy these trucks around the country to customers that need to transfer very, very large amounts of data in the petabyte scale to the cloud or back. All these devices are two-way, of course. And then finally, just briefly talk a little bit about some of the software that we're doing that's kind of, you would call sort of outside the cloud software. And again, you can use your imagination to think about ways that we can either cooperate with a larger ecosystem to support custom hardware that other people build, or we can build some of our own custom hardware and use that to make these services better. And the three that I want to mention just briefly are a service we call RoboMaker. RoboMaker was, again, announced last fall, and we've cooperated with a bunch of other players in the industry, and Intel, Microsoft, and others to take a academic research operating system, a version of Linux based on Debian called Robot Operating System, or ROS, and really commercialize that, bring it up to commercial quality with full regression testing and software management practices. And I think very recently released kind of the first commercial grade version of ROS, and that's really exciting because we have lots of people in the industry now that are all focused on building robots. And robots should be understood very broadly to include anything that, that has sensors, compute, and some ability to react to the environment. Everything from drones to, things that you might normally think of as robots. And so that's been a really successful project that we think has a lot going for it. And again, the ability to support lots of these devices out there with the cloud support for things like software distribution, device management, development environments, and so forth is a powerful thing. Greengrass we've had for a while. This essentially is the ability to take our function as a service, our Lambda environment, deploy that to edge devices, and have those, again, you can test in the cloud and deploy remotely and manage those from the cloud. And that gives you a nice processing or compute model for these remote devices. And then the last thing I'll mention is FreeRTOS. So this has been around a long time. It's a free operating system with a GNU license that has been out there for a number of years. And we, not too long ago, hired the core team to work at Amazon Web Services, and it still remains a completely free and open operating system. But again, we're able to apply kind of commercial grade practices now, do a lot of work on security. We've added features like field updatability, so you can now run and these are this is an operating system for microcontrollers. So these can be very, very tiny and very inexpensive devices. But now you have the ability to do things like over-the-air upgrades of the operating system, which previously wasn't possible. We've also done a bunch of work to do formal verification of the TCP/IP stack to try to make sure that there are not remote execution flaws and so forth, fix a lot of security bugs, and added some ability to call the cloud APIs. We've added a TLS implementation, which is a little edgy for a very, very lightweight device, but it can be done. It has been done, and that way you can have encrypted communication even from very, very small devices, so kind of trying to raise the security bar and make it just, the old saying, like, we want people to fall into the pit of success, right? When you download IoT stuff, it should just be like secure and work really well and be easily manageable and easily field upgradable, so we can avoid some of the problems we've had in the industry in the past where IoT devices were typically, deployed once, never updated, never patched, poorly managed, and then they become a source of botnet problems and so forth and so on. So all these, the latter two, of course, integrate with a cloud service that does all the management and takes care of all that. So again, in this space, I think this message from Amazon Web Services is we want to cooperate with this community and others to provide cloud-managed software that can be integrated with lots of rich new kinds of hardware to do some amazing things, including things maybe that are not easily doable, or at least not maybe economical, using totally general purpose hardware. So, gosh, I talk so fast, I have 3 minutes, so I can take a few questions if there are any. Or I don't know if you have a Q&A. Nope, no Q&A? Okay. Well, thank you very much for your time. I appreciate it.